Right now, somewhere past the orbit of Jupiter, moving faster than almost anything humanity has ever tracked crossing our solar system, there is a visitor from another star that was never supposed to come this close to anything we call home. It arrived without warning. It is leaving without asking permission. And for a few tense weeks in the second half of 2025, some of the most respected names in astrophysics looked at its numbers and asked a question that does not usually get asked about a comet. Was this thing about to hit Mars? Not fly near it? Not pass in the same general neighborhood the way comets sometimes do? Actually hit it. A direct impact on the surface of another planet, calculated down to the kilometer by a Harvard astrophysicist who has spent his career hunting for exactly this kind of moment. And when the James Webb Space Telescope turned its gold mirrors toward the object to figure out what it was actually made of, what came back did not calm the room down. It made things stranger. Stick with me tonight, because this story has more turns in it than almost anything we have covered. And by the end, you're going to know exactly what was real, what was speculation dressed up as certainty, and what is actually sitting in the peer-reviewed record right now about the strangest visitor our solar system has ever hosted. Before we go further, if you want more of these deep, carefully sourced breakdowns of what is actually happening in space right now, hit subscribe and turn on notifications. Because this is not the last strange visitor we are going to talk about, and you do not want to miss the next one landing in your feed. Let's go back to where this actually starts, because the beginning of this story is almost stranger than the ending. On the 1st of July, 2025, a modest telescope system called ATLAS, short for the Asteroid Terrestrial Impact Last Alert System, was doing its usual job at an observatory in Rio Hurtado, Chile. ATLAS was not built to hunt for interstellar visitors. It was built for something far more mundane and far more important to daily life on Earth, scanning the sky every single night looking for any rock that might be heading toward our planet with enough force to matter. That night it caught a single faint point of light moving in a way that did not match anything already logged in its catalog. Within days, astronomers around the world had run the numbers and confirmed what the strange little dot was actually doing. It was not looping around the sun the way every comet and asteroid born in our own solar system does. It was moving on what astronomers call a hyperbolic trajectory, an open, unbound arc that only makes sense if the object came from somewhere else entirely and is simply passing through on its way back out. It was given the name 3I/Atlas. The I stands for Interstellar. The 3 means it is only the third such object humanity has ever confirmed, following a strange cigar-shaped visitor called Oumuamua in 2017, and a far more ordinary-looking comet called Borisov in 2019. Later, when researchers went back through older sky survey images, they found faint traces of this object sitting quietly in the data 55 days before anyone had actually noticed it. It had been there the whole time. Nobody had known what they were looking at until they knew what to look for. At the moment it was discovered, 3I/Atlas was already moving at roughly 137,000 miles an hour, and it was still well outside the orbit of Jupiter. That speed alone told researchers immediately that this was not a local object that had simply been kicked around by the gravity of our own planets. Comets born here get flung into strange orbits by close encounters with Jupiter or Saturn, but they do not arrive already moving that fast from that far out. Something else, some other star system entirely, had accelerated this object long before it ever felt the pull of our sun. By October of 2025, astronomers had worked out its orbital eccentricity, a number describing exactly how stretched and open an orbit is, and it came out to roughly 6.1. For comparison, a circular orbit has an eccentricity of 0, and anything above 1 means the object is not bound to the sun at all. An eccentricity of 6.1 made 3I/Atlas more extreme in its trajectory than either of the 2 interstellar visitors that came before it. Of the 3 confirmed guests our solar system has ever hosted from beyond its own boundary, this one is moving through on the least bound, most aggressive path of the group. Here's where I want you to sit for a second and actually picture the scale of what we are talking about, because the numbers alone do not do it justice. A light year, the distance light itself travels in a full year, is about 6 trillion miles. 3I/Atlas came from somewhere outside our solar system entirely. And by the time researchers led by Martin Cordner at NASA's Goddard Space Flight Center finished analyzing its chemistry using the James Webb Space Telescope, the picture that emerged was almost impossible to process emotionally. Webb's near-infrared spectrograph observed the comet on August 6th of 2025, and its mid-infrared instrument came back for follow-up looks in December after the comet had swung past the sun and begun heating up under fresh solar exposure. What Cordner's team measured was the ratio between 2 forms of carbon in the gas pouring off the object, ordinary carbon-12 and the heavier isotope carbon-13. That ratio shifts slowly across cosmic time as generations of massive stars live, die, and enrich the galaxy with new material. What the team found was a ratio containing far less carbon-13 than anything ever measured in our own solar system, or even in the young planet-forming disks scientists have observed around other nearby stars. Working backward through models of how the galaxy's chemistry has changed over billions of years, the team concluded that this object most likely formed somewhere between 10 and 12 billion years ago, during an early, intensely active period of star formation that astronomers sometimes call cosmic noon. Our own solar system is about 4.6 billion years old. The universe itself is roughly 13.8 billion years old. This means the ice sitting inside 3I/Atlas right now, the ice that James Webb was reading the chemistry of, may have been drifting through the empty space between stars for longer than our sun has existed at all. Cordner told reporters at the time that it might be, in his own words, the oldest object ever observed passing through our solar system. That result was published in the journal Nature in June of 2026, and it alone would have made this one of the biggest astronomy stories of the decade. But it was not the part of the story that grabbed the headlines you have probably already seen. If a story like this is the kind of thing you come here for, go ahead and drop a like on this video right now. It genuinely helps this kind of careful, sourced breakdown reach more people, instead of getting buried under louder, less accurate versions of the same news. Alongside the carbon isotope measurement, Webb's instruments picked up something else in the water the comet was releasing as it warmed near the sun. The ratio of deuterium, a heavier form of hydrogen, to ordinary hydrogen was significantly higher than what is typically found in comets that formed inside our own solar system, with some analyses putting the enrichment at roughly an order of magnitude greater, and other estimates going even higher. That kind of deuterium enrichment only tends to form in extremely cold environments, colder than about minus 243 degrees Celsius. Combined with the carbon isotope data, it painted a consistent, coherent picture. This object formed somewhere unusually frigid and unusually long ago, likely in a part of the galaxy astronomers associate with the older, more scattered population of stars known as the galactic thick disk, rather than the flatter, younger disk our own sun belongs to. And then Webb, alongside NASA's newer SPHERE-X mission, looked at what gases were actually pouring off the object as it approached the sun and warmed up. In a typical comet born in our own solar system, you would expect water vapor to dominate that outgassing, since water ice is the most common frozen material comets carry. That is not what the instruments found here. The coma of 3I/Atlas, the glowing cloud of gas and dust surrounding its icy core, was overwhelmingly carbon dioxide, making up roughly 95% of the detected gas, with water accounting for only a small fraction. Webb also picked up tiny water ice particles and carbon monoxide gas mixed into the coma, suggesting a genuinely layered, complicated structure of frozen materials all warming up together as the comet swung closer to the sun. A carbon dioxide-dominated coma at this particular distance from a star is unusual. It suggests the object condensed somewhere extremely cold, colder than the region where our own solar system's comets originally formed, and a part of a long dead stellar disk where carbon dioxide ice could survive more easily than water ice ever could. Researchers who authored the paper describing this detection, published as a preprint in the closing weeks of August 2025, described it as direct evidence that 3I/Atlas came from a formation environment genuinely different from anything in our own solar neighborhood. Now here is where the story stopped being a quiet chemistry puzzle for specialists and started pulling in headlines from every corner of the internet. In October of 2025, a research team using the UVES spectrograph on the European Very Large Telescope in Chile detected something in the comet's coma that nobody was expecting. A plume of nickel gas, later corroborated by additional data from the Keck 2 telescope in Hawaii. On its own, nickel vapor is not shocking. It has been detected before in a handful of solar system comets, including Borisov, the interstellar visitor that came before this one. What made this genuinely different was what was missing alongside it. Every previous time nickel vapor has been detected venting from a comet, it has been accompanied by iron vapor, because the two metals are forged together deep inside dying stars and supernovae, and they travel through space chemically bound to each other, sometimes described by researchers as cosmic twins. In 3I/Atlas, the nickel signal was strong, and the iron signal was almost entirely absent. Astronomers scrambled to explain how that was even chemically possible. Comets are generally far too cold, even close to the sun, for solid metal grains to sublimate directly into gas. Something else had to be releasing the nickel through a different pathway entirely, most likely a fragile nickel-bearing molecule, something like a nickel carbonyl compound, that breaks apart under weaker sunlight than whatever is holding the iron locked in place. It is a real, if genuinely unusual, natural chemical mechanism, and most astronomers studying the object consider it the most plausible explanation. But it is worth being honest that at the time of the detection, Researchers had not fully confirmed exactly which compound was responsible, and several published papers described the finding using words like extremely puzzling because nothing in the solar system comet record looks quite like it. Faint traces of this same nickel-dominant pattern, though far less pronounced, were later found in Borisov's older data too, which suggests this might be a genuine feature of objects that formed outside our solar system, rather than something unique to this one comet alone. It was against this backdrop, an ancient object, a strange chemical signature, an orbit steeper and more extreme than anything seen before, that the headline you actually clicked on tonight started to take shape. Because in early September of 2025, Harvard theoretical physicist Avi Loeb, who has spent much of his career searching for potential signs of extraterrestrial technology, and who led the research group behind the Galileo project, published an analysis that reframed everything the public thought it knew about this object. Loeb pointed out that the comet's trajectory would carry it remarkably close to 3 planets during its passage through the inner solar system: Venus, Jupiter, and most dramatically Mars, passing within a little over 18 million miles of the red planet on October 3rd of 2025. Loeb calculated that the probability of a naturally formed interstellar object arriving on a path that threads this close to multiple planets, while also staying hidden from Earth-based telescopes at the exact moment it rounded the Sun, was vanishingly small, a figure he described in one paper as roughly 0.005%. He argued that this level of precision was, in his words, worth taking seriously, as evidence the trajectory might not be entirely accidental. And then came the number that turned this from an academic curiosity into a genuine viral moment. Working with a colleague, Loeb calculated that if the object received an additional push of roughly 10 kilometers per second of velocity sometime in September of 2025, whether from an engineered maneuver or an unusually violent natural outgassing event, its path could be redirected just enough to bring it into direct collision with the surface of Mars as early as that October. That single calculation, an interstellar object was on a trajectory that, with only a modest course correction, could put it on a collision course with another planet, was the spark that lit up headlines across the internet describing the object as being on, quote, a collision course with Mars. Here is where I need to slow down and be completely honest with you, because this is exactly the point where a fascinating, legitimate scientific question gets bent into something the actual data never supported. What Loeb published was not a confirmed collision course. It was a conditional calculation, a hypothetical, built on the premise that if the comet received an extra, unexplained burst of velocity, then a collision became mathematically possible. The James Webb Space Telescope never confirmed an impact trajectory. No space agency on Earth, not NASA, not the European Space Agency, ever issued a warning about a Mars impact. What actually happened, measured, tracked, and refined continuously by observatories and spacecraft all over the solar system, was something far calmer and, in its own way, far more remarkable than the collision headlines ever gave it credit for. If you are the kind of person who wants the real, careful version of a story like this instead of the exaggerated one, that is genuinely worth a comment below telling me what surprised you most so far, because it helps shape which stories we chase down next. On October 3rd of 2025, 3I/ATLAS made its closest approach to Mars, and it passed at a distance of approximately 29 million kilometers, a little over 18 million miles. To put that in perspective, that is roughly 76 times farther away than the distance between the Earth and our own moon. It was close by the standards of interstellar space, close enough that it became a genuinely exciting scientific opportunity. But it was never anywhere near close enough to represent an actual impact threat, and the trajectory data collected throughout that encounter never once showed it trending toward the surface. Because the comet passed so much closer to Mars than it ever would to Earth, the fleet of spacecraft already stationed at the red planet suddenly became the best observation platform humanity had for this object. The European Space Agency's Mars Express and its ExoMars Trace Gas Orbiter both turned their instruments towards the comet during the flyby, capturing images and data from a vantage point no Earth-based telescope could match. NASA's Perseverance rover, sitting on the Martian surface itself, along with multiple orbiters circling the planet, captured images of the comet passing by, marking the closest any spacecraft had ever gotten to an interstellar object up to that point. The European Space Agency's JWST spacecraft, which was already in transit toward Jupiter's icy moons, used the opportunity to point its own cameras, spectrometers, and particle sensors at the comet as it passed nearby, adding yet another independent vantage point to the growing dataset. None of these instruments, positioned closer to this object than anything humanity had ever managed before, recorded any indication of an impending impact. And what they recorded was a natural comet, outgassing, tumbling gently, and continuing along the exact hyperbolic path predicted by ordinary orbital mechanics. This is actually where the story becomes genuinely interesting again, because the trajectory data gathered during that close Mars encounter ended up playing a direct role in settling the larger debate Loeb had opened. A team of researchers led by Daryl Seligman, an astronomer at Michigan State University who has studied the comet extensively, along with Marshall Eubanks and other collaborators, used long baseline astrometry, essentially combining extremely precise position measurements of the comet taken from multiple spacecraft spread across the solar system, including NASA's Psyche mission and the European Space Agency's Mars Trace Gas Orbiter, to measure something called the comet's non-gravitational acceleration. Every comet that is actively venting gas experiences a tiny push from that outgassing, a bit like a very slow, very gentle rocket effect, and that push causes its path to deviate very slightly from what pure gravity alone would predict. By measuring that deviation with extraordinary precision using observation points separated by enormous distances across the solar system, the team was able to directly test whether the object's trajectory showed any sign of an artificial, engineered course correction, the kind of maneuver that would be required for the collision scenario Loeb had raised to actually happen. Their conclusion was unambiguous. The acceleration they measured matched almost exactly what you would expect from ordinary cometary outgassing, the same physical process that nudges the path of any active comet as ice sublimates unevenly off its surface. There was no evidence of a deliberate thrust, no unexplained velocity change, nothing pointing toward an engineered trajectory adjustment of any kind. Seligman's team summarized their findings bluntly, describing the object as, in their words, exotic and wonderful, and also a comet. It has obvious cometary outgassing with a non-gravitational acceleration to match, they wrote, and claiming that it is also a spacecraft simply does not fit the measured data. Loeb himself, to his credit, never claimed certainty. In the papers where he raised the Mars collision hypothesis and the broader idea that the object might be artificial, he explicitly assigned it a probability rather than a confirmation, at one point putting the odds of an artificial origin at around 40%, a number that gave the theory enough weight to generate enormous public attention while still technically hedging against being proven definitively wrong. Other astronomers were considerably less generous in their assessment of that reasoning. Researchers analyzing Loeb's statistical claims pointed out a deeper problem with the entire argument. With only 3 confirmed interstellar objects ever observed passing through our solar system, there simply is not enough data to know what a normal, unremarkable trajectory for this kind of visitor is even supposed to look like. Calculating the probability of an orbit being suspicious requires knowing the full range of trajectories interstellar objects can plausibly have, and with a sample size of 3, that range is essentially unknown. A team of independent researchers ran large-scale simulations testing how often a randomly generated interstellar trajectory would happen to pass within roughly 100 million kilometers of at least one planet during its transit through the inner solar system, and found that this kind of coincidental close approach happens far more often than Loeb's headline probability number suggested, once you account for how many different planets and configurations could have technically qualified as a close pass. In plain terms, threading somewhat near a planet on your way through a solar system full of planets turns out to be a lot less rare than it sounds when you first hear the number. If you have made it this far into the story, go ahead and hit subscribe if you have not already, because this is exactly the kind of layered, evolving science story where the full picture only comes into focus over months of new data, and we are going to keep tracking it as more comes in. By the time 3I/ATLAS made its closest approach to the Sun, on October 30th of 2025, passing at a distance of about 130 million miles just outside the orbit of Mars, the collision panic had already largely faded from the mainstream conversation, replaced by the far more interesting and far better supported chemistry findings the telescopes were actually confirming. At that moment, Earth was positioned on the opposite side of the Sun from the comet, a geometric alignment that meant ground-based telescopes could not observe it directly during its hottest, most active phase, a period astronomers call solar conjunction. It reemerged into view in early December of 2025, giving observatories around the world a fresh window to study it before it grew too faint and too distant to observe in detail. On December 19th of 2025, the comet made its closest approach to Earth, and even at that moment, widely covered across international news outlets, it never came anywhere close enough to represent any kind of threat, passing at a distance of roughly 270 million kilometers, close to 1.5 times the distance between the Earth and the Sun, or more than 700 times the distance between the Earth and our own moon. NASA and the European Space Agency were both explicit and completely consistent throughout the entire encounter. Comet 3I/ATLAS posed no threat of impact with Earth, Mars, or any other body in our solar system at any point during its passage, and its trajectory never deviated from the predictable path expected of a natural comet governed by gravity and gentle outgassing. So where does that leave the actual headline? the one claiming James Webb confirmed a collision course with Mars. The honest answer is that it never happened, and it was never something the James Webb Space Telescope or any other instrument confirmed. What Webb confirmed in careful, peer-reviewed, published detail was something arguably far more scientifically valuable than a doomsday collision story, because it gave researchers their first direct chemical sample of material that condensed around a completely different star, under completely different conditions, billions of years before our own solar system even began to form. What Avi Loeb raised was a legitimate, mathematically grounded question about a genuinely unusual trajectory, one worth investigating seriously, which is exactly what a large, international team of astronomers proceeded to do using every spacecraft they could point at the object. And what those investigations found, using precise measurements from multiple spacecraft spread billions of miles apart, was a natural comet behaving the way natural comets behave, with no evidence of an engineered course correction, no evidence of an artificial thrust, and absolutely no trajectory that ever pointed toward an actual impact with Mars, Earth, or anything else in our solar system. The nickel and iron anomaly remains real and only partially explained. The extreme age of the object remains one of the most remarkable confirmed facts in the modern history of astronomy. The carbon dioxide-dominated coma remains a genuine puzzle about how and where this thing actually formed. But the collision course, the part of the story that got this video its headline, was never something the data supported once you followed it all the way through to the published, peer-reviewed conclusion. It is worth pausing here to talk about why this particular story spread the way it did, because it is a pattern worth understanding for every space story you encounter from here forward. A legitimate scientist raised a genuinely interesting statistical question, framed carefully with appropriate hedging and probability language. That nuance travels poorly. Headlines compress conditional, probability-weighted hypotheses into declarative statements, because declarative statements get more attention than careful ones. Somewhere between a research paper describing a 0.0005% probability calculation under a specific hypothetical velocity change, and the video title that pulled you in tonight, the careful, hedged scientific language quietly disappeared, and what was left behind was a flat, confident claim of a confirmed collision course that is close to a universal pattern in how space discoveries move from a telescope to a paper to a headline, with a little nuance shaved off at every step. The real version, grounded in the published Nature paper, the Mars orbiter data, and the astrometry that ruled out an artificial trajectory, is more interesting than the collision headline anyway, because it tells you something true and permanent rather than something dramatic that turned out not to happen. Here is something worth sitting with for a moment, because it connects everything we have talked about tonight into a single, coherent picture. Every comet born inside our own solar system formed from the same disk of material that eventually built the planets, which means studying them mostly tells us about our own local chemistry, the specific conditions that existed here around our specific star 4.5 billion years ago. 3I/ATLAS is fundamentally different. It is a physical sample of material that condensed around a completely different star under different temperatures at a completely different point in the galaxy's long history, and it drifted through the empty space between stars for potentially 10 billion years or more without ever being disturbed by any star's heat until it stumbled into ours. That gives researchers something they have essentially never had before in the history of planetary science, a direct chemical comparison point to test whether the physical process of building icy bodies, and eventually planets, works the same way everywhere in the galaxy, or whether it varies significantly depending on where and when a particular star system happened to form. The nickel and iron anomaly, specifically, is already forcing cometary scientists to reconsider long-standing assumptions about how metals get locked into, or released from, cometary ice at extreme distances from any star, assumptions that were built almost entirely on a sample size of comets that all formed in our own cosmic backyard. This is not a discovery that rewrites the fundamental laws of physics. It is a discovery that finally gives astronomers a genuine outside data point. And outside data points are exactly how you find out which of your working assumptions were actually just local habits all along, dressed up as universal rules because nobody had anything else to compare them to. As of right now, in the summer of 2026, 3I/ATLAS is somewhere well past the orbit of Jupiter, continuing to move outward, away from the sun and away from every planet it briefly threaded past, at more than 60 kilometers a second, carrying chemistry that was locked into ice before our own sun had even finished forming. It will never slow down, it will never turn around, and it will never pass this way again. Every instrument that was ever going to get a close look at it has already had its turn, from the ground-based telescopes in Chile and Hawaii, to the orbiters circling Mars, to the James Webb Space Telescope parked nearly 1 million miles from Earth, patiently reading the chemical fingerprint of a single beam of ancient starlight bouncing off an object older than our entire solar system. What is left behind is not a mystery solved and not a threat avoided. because there was never truly a threat to begin with. Only a genuinely rigorous scientific question that got asked, tested, and answered using real instruments and real data rather than speculation left to run wild in the comment sections of the internet. What is left is a complete data set, sitting in the archives of Hubble, Webb, and a dozen ground-based and Mars-based observatories, a permanent record of a piece of another part of the galaxy that happened to drift close enough for humanity to actually measure it once before it disappeared back into the dark it came from. And this will not be the last time this exact story plays out. Scientists at the newly operational Vera Rubin Observatory in Chile, home to the largest camera ever built for a wide-field, fast-cadence sky survey, expect to find many more interstellar objects in the coming years, possibly dozens over the next decade alone. Unlike the ATLAS survey, which was primarily built to hunt for asteroids that might threaten Earth and only found this comet as an accidental byproduct of that broader search, Rubin's entire survey strategy is specifically designed to scan enormous swaths of sky repeatedly, night after night, dramatically increasing the odds of catching the next fast-moving interstellar visitor early in its approach, while there is still enough time to redirect other telescopes and potentially even spacecraft toward it before it passes through and disappears for good. Researchers already unofficially refer to whichever object turns up next as 4I, whenever and wherever it happens to be found. The 3 interstellar visitors confirmed so far, Oumuamua, Borisov, and 3I/Atlas, are almost certainly not rare in any absolute sense. Researchers increasingly believe objects like these have been drifting past our sun since the very earliest days of the solar system's formation. We simply lacked the technology and the awareness of what to look for to notice them until the last decade. Now that the technology exists, the pace of discovery is expected to accelerate substantially, and the next headline promising a collision course, an alien probe, or a confirmed threat is, statistically speaking, only a matter of time.